Oh, oops. Here we go. Okay, so impulse and momentum is the name of the technique, and what it does is you need to know what these things are. Impulse is the time integral of force, and I'll have to create the notes as I go along here because it wipes those out as well. But anyway, impulse is the time integral of force, and momentum is the mass times velocity of the center of mass. Okay, they're vector quantities because force can be up, down, sideways, left, right, whatever, and so momentum is also a vector quantity. So it's mass times the velocity. So velocity's got direction as well. The formula is impulse will equal the change in momentum, and in fact, this is the way Newton. My understanding, I haven't read his original papers, but what I was taught is that's what Newton initially said, is that it's the impulse that equals the change in momentum, not F equals ma. Okay, but whatever, right? The method is best used when the impulse is known. Okay, so I'll show you what I mean by that. So typically, it's like work. If you can't get the work and energy, if you can't get the work done, don't even bother with the energy. So impulse is going to be similar. You can use them, but there's really no advantage to you unless you know what the impulse is, okay? What I've seen people do is, and I'll show you some examples here in a little bit. They use impulse to try to understand why things do what they do. And I've got some videos to show you that. Or what I've done is, in the laboratory, you'll measure the impulse. So what you'll do is you'll get a graph of force versus time, and you measure the impulse. And by measuring the impulse, you can determine what's happening to the system. So that's where it's most commonly used. There's also something called angular impulse, which is used for rigid bodies. Angular impulse, I like to call it moment of momentum, because that's what it is. Angular impulse is the time integral of the moment. So if you can find the time integral of force, then hopefully you can find the time integral of moment. It's used for rotational things. Angular momentum, I like to call it moment of momentum because that's how you calculate it, is the moment of mass times velocity. So you find the momentum, and then you simply take the moment of it. You know how to take the moment of a force, right? You take the force and you take the perpendicular distance. You're going to do the same thing to get moment of momentum. You're going to take the momentum and you can take the perpendicular distance to it, okay? So anyway, that's basically what it is. The next concept that you're going to use is this concept of impulsive forces. An impulsive force is very large. It occurs over a short time period. For example, if you hit a baseball, the time that the bat is in contact with the ball is very, very short, and the force between the bat and the ball is very large. That's an impulsive force. Typically what happens when you have impulsive forces is you ignore everything else that's happening. There's other forces on there. If they're not impulsive, you just ignore them. Why? Because the time period is so short that they don't have the time to impact, bless you. They don't have the time required to affect the motion. And so when you're doing problems that involve impulsive forces, we're going to ignore everything except the impulsive forces. Collisions will have impulsive forces. So if you take a ball and you bounce it on the floor, the moment that it begins to touch the floor to the moment that it releases from the floor is an impulsive force. Okay, it's very large compared to the gravity and everything else. It's very large, and it occurs over a very short period of time. So we'll ignore the gravity, we'll ignore the weight, the friction, everything else is going to be ignored during that time of collision. If you're driving your car down the highway and, God forbid, you hit an embankment, you're going to get these huge forces. The huge force is what crumples up your car, it's what damages your body, and they occur over a very short period of time, very large, very short period of time. Okay? And in fact, if you are looking for highway safety, the whole idea behind highway safety is to get the energy that's in your body out of your body in a very safe way. That's why they have airbags, that's why they have all the restraint systems, so that you get the energy, because you got kinetic energy going down the highway. You hit something, that energy is going to come out and come out quick, because 1 second you're going 60 miles an hour, the next thousandth of a second, you're going 0. Well, where did your energy go? It breaks your bones, it breaks your liver, it destroys your body. So what you have to do is get that energy out of your body and get it somewhere else. You can't just throw it away. You got to put it in something else, and you got to do it very quickly. And that's what the whole idea is. I don't know if you've seen these, from the aerial view. You'll have a roadway, and there's a guardrail, and if you look at them, they'll have this little device over here, kind of like, it's kind of shaped funny like that. And I don't know if you've seen those, but what they do is if you hit those edge of the guardrail, what it does is this thing will move backwards as you push it, and it coils up the guardrail. So maybe you've seen, you're driving around and you see these guardrails and they're kind of coiled up. What happened was somebody hit that, and they've designed it so it'll coil that metal, which takes work. And the reason they're doing that is they're taking the energy out of your car and putting it into the coil of that metal, so that you release the energy. Some time ago in East Texas, they used to take these orange barrels, and they would fill them with water, especially for temporary things. And the reason they would put the water in there is if you hit the barrel, what you want to get the energy out of the car and into something else. So what it would do is you'd hit that barrel, and then the water would spray, and that's puts the energy into the water, so it would slow your car down much safer. Now, I don't know about here because water's kind of precious, but East Texas, no big deal, and you see these people going around filling them, making sure the barrels are always full. But anyway, that's the idea of impulsive forces. You want to get rid of them. Also, I'm sure you've seen this magic trick where you take the magician takes a table, let's say on the side, and he has a tablecloth over here, so the tablecloth is hanging off to the side, and you stack dishes on here. You've seen that, right? And then they come over and they grab the sheet, and they pull the sheet out, and the dishes stay there. How does that work?
Inertia.
What do you mean inertia? Give me some more information.
The object wants to stay at rest at all times.
They stay at rest, but why do they stay at rest? Because I'm pulling the tablecloth out from under them. Huh?
You break static friction.
What do you mean you break static friction?
Well, the limit for how much force is in.
Okay, so but you got friction. How come the dishes don't come with you? I mean, you break the static and you become kinetic, I agree, but how come the dishes don't come? What would happen if you took the tablecloth and you pulled it real slow? What would happen then? Would they come off with you? Okay, so why is it that it's important that you go pow?
Certain applying force in a short amount of time.
Right, what you do on the tablecloth is you apply an impulsive force, okay? It's you go kapow, so it's a large force, right, over a short period of time. Got it? Large force over a short period of time. That's the force that's on the tablecloth. So what is the tablecloth's response to a very large force? You get a very large acceleration. Or in this case, for momentum, you would get a very large change in momentum. Impulse will equal change in momentum. So what happens is by popping that tablecloth, you give a large momentum to the tablecloth. And because the tablecloth is lightweight, man, it goes fast. Get the idea? Mm-hmm. What about the dishes? What's the force on the dishes? Is it impulsive? It's friction, right? Mm-hmm. What's friction? And you break the friction. You're right. So what is friction? Now the tablecloth is broken the friction. Mu K times what? N? Is N impulsive? Is it huge? No. Pow, like that, right? I mean, is it a large force? Pow. No. N is whatever the weight of the dishes are. Not a big deal. Right? How long is the tablecloth underneath the dishes? Long time, short time? Short time, right? If you pop it out of there, the tablecloth moves fast, right? So it's not under the dishes for very long. So what you have is a modest amount of force, mu n, for a very short period of time. Okay? Impulse is the force times time. Right? So the force is mg times mu k, modest amount, times a very short period of time. How much impulse do you have? Large or small? Small. He has small impulse. Okay? So impulse equals change in momentum. How much change in momentum do you have on the dishes? Large or small? small. So do the dishes move very much? No. So the trick is you pop that tablecloth out quick before the dishes have a chance to respond. Because if you pull it slowly, they'll come with it. Get the idea?
Yeah.
Okay. Could you ever use that concept for something useful? I mean, we're engineers, right? I mean, we need to understand how things work, and then we need to exploit that. Exploitation may not be a good word, but, right? Isn't that what engineers are kind of, isn't that what you expect that engineers do? You say, here's how things work, okay, then I'm gonna build an airplane. Here's how things work, okay, then I'm gonna make highway safety. Get the idea? Can we use this magic trick concept? Well, let me show you a video. Okay. Hopefully this will work. Nope, tell you what. Nowhere to go. Okay, so now can you see what's happening? You see the bolt? The bolt's not moving. You see the bolt moving? And this is, you see the spiral coming up? And those are just screws, you just pour them in there. How does that work? What do you mean vibration? Give me some more ideas. Vibration, well, you can hear it's vibrating, right? So it's doing something. Is it vibrating like this? Back and forth? What's it doing? Huh? Okay, in which direction? What's it doing? Up and down this way? What's it doing? Side to side? What's it doing? Spinning? This way? Is that what it's doing? Would that explain why these screws are moving? Huh? Why is it going this way? It's going this way, back and forth. Twisting like this. Why does the screw move when we go like this? That's what the bolt's doing. You don't see it because it's going really, really fast. But it's doing this. Kind of. What's happening? With that magic trick. What do you mean by it? What's happening? What it's doing is it's applying an impulsive movement in one direction. Wham! Like this. So do the screws move? There's the dishes on top of the screws are the magical dishes, right? And so you apply an impulsive moment. Bam! In one direction. Screws don't go very far that way. Then what do? Slowly bring it back. Now it's not impulsive force, correct? So what do the screws do? They go with the bolt. And then all of a sudden, wham, and pull the bolt out from under it again. And then you slowly go back. Get the idea? Wham! Slowly go back. Okay? So what you see, because you can't see the individual rotations back and forth, what you see is, it looks like these guys get up and just walk up the ramp. Isn't that cool? This is called a bowl feeder, B-O-W-L feeder. They're used in factories all the time. So, for example, you want to build a robot, and in fact, it works for everything. There's a little piece of dirt or something coming up here. You can see it in there. Some dust, and it does the same thing as screws do. But anyway, suppose you got a robot and he wants to pick up the screws. You don't want the robot to reach in there and start finding the screws. You want the robot to go to a known location, pick up the screw, and put it into its hole. Okay, and so what you do is you use a bolt feeder and you put, if you watch it long enough, you see that dirt? Go around. Anyway, the screws will come up and position themselves right along in this slot right here. And just sit there and wait for the robot to come over and pick them up. So this is a bolt feeder. It's used all the time. The point I'm trying to make is when I teach you something in your class, you got two reasons. One, you got to pass the class. how do you know, I can't teach you all of the ways that you can be clever and come up with new ideas. Because if I could teach that, I would do it. And I would be making the room in your body, not you. Right? So what I'm trying to do is say, you see, these concepts I'm trying to show you, they have some utility. It's up to you to be clever and to say, you know what, nobody's ever thought of this. I'm going to do this, and I'm going to make money. Or I'm going to help mankind, whatever floats your boat. Okay? But the point is, this is not just textbook stuff. This is real stuff. Use it for something. What? I don't know. Got the idea? Any questions about bowl feeders? Okay. Let's see if I can figure out how to stop it. Bingo. That was easier than I thought. Okay. Let me see back on the other one. Okay. How does this one work? Tell you what, let's do a problem, and then I'll come back and ask you how that works. Let's do this problem right here. Because you do have to pass the class. So let's try to make some sense out of this. Okay. All right, so the car A has a weight of 4,500 and is traveling to the right at 3. Meanwhile, a 3,000-pound car B is traveling at 6 to the left. Cars crash head on and become entangled so they don't bounce off. They just, boom, smash up together. Determine the common velocity just after the collision. Assume that the brakes are not applied during the collision. Okay, so here we go. What I'm going to do is I'm going to say, all right, what kind of problem is this? Is this an energy problem? That's what I would suggest you do on the final, is say, is this an energy problem? Because if it is, then energy problems usually take a lot less time, and you want to grab a hold of that and go. Is it an energy problem? What questions should you ask yourself to say if it's an energy problem? Is it a time spanner? Not really. I mean, I guess it's a before and an after, so it's a small time. Okay. Can you get the, what's the second question? Well, the first question was, can you get the work? Right? Can you get the energy that's coming and going? And what would you tell me? Yes or no? No. Why not? There's a lot of energy that's, I'll call it lost. It's not really lost. It moves into something else, and I'll tell you what it moves into in a minute. You have energy, kinetic and potential energy, and it disappears during a collision. Okay? It disappears during a collision. You don't believe that? Okay, drive your car down the road at 60 miles an hour. Do you have energy? Yeah. Hit an embankment. Do you have energy? Kinetic energy? No, you do not. What happened to the energy? You did not destroy it. What happened to the energy? It goes from, yeah, in your car, let's not talk about your body, because your spleen is probably outside your body, but, okay, talk about the car. What happened to the kinetic energy of the car? Well, the kinetic energy of the car went into the work it requires to bend up the metal. That's why your car bends up, okay? So the kinetic energy of the car went into something else. It's not lost, it went into something else. There's a lot of energy that's required to bend metal. You just did it. You just didn't do it effectively, because now it looks like a big ball of whatever. Get the idea? Okay, so when these guys collide, do you know how much energy is lost? No. So if you don't know how much energy comes out, you better not try to use energy, because you don't know the work. You get the idea? So anytime you have a collision, you're not going to want to use energy, because you're going to lose energy and you don't know how much. So it's not energy. Okay, could it be an F equal MA problem? It might be, okay? It might be, but what I would suggest is say, okay, maybe it's an impulse and momentum problem. Okay, maybe it's an impulse and momentum. Here's what you want to do. Is it possible that I can define the system some way where I know what the impulse is? What is impulse? It's the integral of force and time. Okay, so is it possible? Well, here's what I'm going to do. If I take car A and B in a system together, okay, if I take an A and a B in a system together, what are the forces that I would have to draw on the free body diagram? A and B are in there together. Do I draw the weight of A and B? Yes. Why? Because A and B are in the diagram. The earth is outside the diagram. Do you draw those? Do you draw the normal forces under the tires? Yes, for the same reason. If there was friction, would you draw the friction? Yes, same reason. There's force between A and B when they collide, isn't there? Man, it's big. Do you draw that? No. Why not? Inside, inside. Okay? So what I'm going to do is I'm going to say, okay, I'm going to take A and B together in a system, and then I'm going to use impulse and momentum, because what I'm going to do is say, when they're colliding, that force between them is impulsive, and it's going to occur over a short period of time. You agree? Just like that magic trick, if you have an impulsive force, you might as well forget all the others. They're just not going to impact you. No pun intended. It's not going to affect you. Get the idea? Right? So what I'm going to do is I'm going to say, okay, I'm going to take A and B together, and I'm only going to be interested in impulsive forces. So, is the weight impulsive? Those cars are heavy. Is it impulsive? No, it's not a huge force. It's heavy. But can you imagine the force between these cars? Oh my goodness, that's going to be a lot greater. Does the weight of your car bend your car? No, you see, it's not that large. But will these collisions bend your car? You bet it will. You see how much larger they are? So I'm going to ignore the weight. What about the normal force under the tires? Same? Is it huge? No. It doesn't bend your car. Not like those collision forces. You get the idea? Okay, what about if there was friction? Would I include it? No. Why not? Man, even though you think it's big, it ain't bending the car. Get the idea? So what I'm going to do is I'm going to say, for that brief moment that they're in a collision, I'm going to ignore all those little bitty guys. I'm only going to deal with that one. Okay, then what's the forces on it? If you take A and B together, there's A, there's B. What are the impulsive forces? You got any? The force between them, right? Do you draw that? No. Why not? A and B are in there together. That's why not. You got any other impulsive forces? Any others? No? Okay. The impulse equals 0. Right? The impulse is 0. Of the impulsive forces, the impulse is 0. Because it occurs for such a short period of time, who cares about that weight? It's not going to move that car very much. Right? It's, split second, man. I'm sure you've seen collisions. Maybe you've been in one. Right? Okay. So Newton said the impulse, 0, equals change in momentum. What is change? I told you what it was in energy. What's change? It's always what? Final minus initial. So change in momentum. So what I need is after the collision, what's the momentum? Before the collision, what's the momentum? And I just subtract the two. Got it? Okay, so here we go. After the collision, the two guys are, meshed together. And momentum is equal to mass times velocity. So that would be after the collision. I've got 4,500 plus 3,000. And is that mass? Okay, so I'm going to divide by G. Is that mass? Yep. How fast are they going? We don't know. Let's call that V. Okay. Which direction are they going? Right or left? You don't know? Okay. Which way do you want? You're going to guess. To the left? Okay. You want right positive or left positive? Right positive? Okay. So here's positive. You just told me, you think they're going to go left. Okay, fine. Then what am I going to put in here? Plus or minus? I'm going to put in a minus V. Now what I would have done is I would have said, I'm going to put in plus V, right? Why? Because I have a terrible memory. and I'd always do the same thing so that when I get the answer, I don't have to look back and say, what did I do this time? Because I always do the same thing. I always say, even if you know they're going left, put it in as positive. Okay? And then you're expecting to get a negative number. And then you say, no big deal. Okay, but anyway, that's what you wanted, that's what you got. And then I'm going to say minus. Why am I going to say minus? Final minus initial. So now I'm going to put a little big bracket here. Let's see. Let me get rid of this guy because I won't have space. Okay, so now here we go. Minus. Here comes the initial. Initially, they're not combined, are they? So I'm going to add up their momentum separately. Let's do A. A is a mass of, or weight of 4,500. 4,500 over G, that's his mass. What is his initial velocity? 3, is it positive or negative? Positive? Okay, so times 3. That is that guy. Okay, how about B? How much mass has B got? 3,000 over G. How fast is he going? 6, positive or negative? Negative. So I'm going to say, okay, he's got a negative 6. What is that? That is final momentum minus initial momentum. Got it? Okay. What's in the parentheses right here, that's the initial. This stuff that is right here, that's the final. So it's final minus initial. See how easy that is? How many unknowns you got? 1. How many equations you got? 1. Can you solve for the V? You better be able to. The positive tells you what? You're right. Which way did you say you thought it went? Left? Okay, if you get a positive number, you're correct. It's going left. If you get a negative number, what does it mean? It means you're wrong. What did you think it did? You thought it went left? You're wrong. It goes to the right. Got it? Okay, any questions about that? Okay, they're all pretty much like that. I'm going to do some more problems. But before we do, let's take a look at this one. I want you to tell me why this works. How does that work? See what it's doing? Falling over. How in the world do you get a little toy like that to flip over? Huh? A large force? Okay, so at least he's catching on to something here, right? Ah, yeah, it's impulsive. You're right, there is a large force. What it does is it winds up and then it pulls a pin back and a little plastic part inside pops up real fast. Okay, so it's just a real quick force. But how in the world does it flip over? Why in the world is it flipping over? It's a large force. Why does a large force cause it to flip over? Okay, so what he's saying here is that, well, it's not exactly in the center. So let's see. Right? So basically, if you have a mass, something like this, and you put a mass here and you shove this guy up, is that large force in the center? Okay, so what's going to happen is you're going to have some momentum right here. So this guy right here, he's going to have some momentum. And here's the center of mass. Let's say the center of mass is right here. Doesn't that momentum have a moment around the center? Does it or no? Okay, so what will happen is if you have a moment, right, an impulsive moment, so here's this force that's over here pushing on this mass, that's an impulsive moment, right? That impulsive moment is going to create a change in moment of momentum. So what will happen is you'll have a flipping. Let me show you another simulation. Whoa. No, that's not what I wanted. Come on. There we go. That's the one I want. So, where is it? Yeah, there we go. Okay, this is a computer simulation. Let's see if I can rewind it. Stop. There we go. The two green boxes are just together. I've pulled them apart so you can clearly see that the center of mass is kind of in the middle of the green. Okay. And then there's that red spring, and the light blue box is just another little piece of plastic, another little mass. And so what happens is if it'll rewind and replay. Let's see.
It'll do it.
Will it? Okay. Just have patience, okay. That's what I'm not known for. Ask my wife, she'll tell you. Thought you said it would replay. Okay. Did you see what happened? Right? The spring pushes that mass up. So what it does is it creates momentum, right? Momentum, the blue guy's got momentum, and he's off center. So he has a moment of momentum, right? A moment of momentum. So what happens is he begins to flip, right? What if this blue mass was right over the center of mass? What would it do? It would just jump straight up, right? How could you use something like this? You could build toys, right? And in fact, if you hit the internet, they sell these things for like $5 each. They're dirt cheap, right? They probably cost them 50 cents to make, and they're going to sell them to you for $5. And people will buy them because they're fascinating, right? I mean, for a little while. And then you say, well, you know, that's enough of that. But, right? So, but there's other applications for that as well. One of the more interesting ones that I ran across is the stabilization of the space station. At one time, you know, they didn't fly this, but what they did was they said, you know, we've got a space station, and then we're flying. Here's the Earth, and it's real long, and they were going to fly it this way. Okay, so it was going to fly in orbit like that. And there were reasons why they wanted to do that. But anyway, they wanted to fly it straight up like that. Well, what would happen is over time, there's a little bit more drag here, a little bit more air here than up here. Not much, but there's a little bit. So what would happen if you had an unbalanced drag on the bottom and the top? Yeah, there's a moment. So eventually what would happen is the station would begin to rotate, right? And so it kind of would tumble. Make sense? Okay, so how do you stabilize that? You counteract it. How are you going to counteract it? Well, one of the things they could do is they could put a thruster up here, right? Right here. So let's see, it's going to tumble this way. So what they would do is they thrust back this way. So they fire a rocket, right? You know, make up for it. Maybe I drew it the wrong way, but you get the idea. You fire a rocket, okay? The problem with the rocket is, you know, you got that propellant. You got to get it up there. It's going to be expensive, okay? So the other idea that this engineer had is he's going to, you know, you've got water up there for the astronauts. Okay, so what he's going to do is he's going to take a pipe. He's going to put it in a circle like this, and he's going to put a pump. He'll probably put the pump here. And what he does is he circulates the water. Okay? So what would happen is, you know, you get this drag right here. Well, that's a moment, right? That's a moment, angular moment, right? So what they would do is they'd say, well, that has to equal the change in angular momentum, moment of momentum. So what I want to do is I want something to spin. So what it'll do is instead of the station spinning, they'll spin the water, right? And then the station stays straight up. Clever idea, isn't it? Okay? Real clever idea. They also use them on the ground when you're trying to stabilize, you know, rotating machinery and things like that. They'll do very similar things. But anyway, so the problem with this is after a while, the water is whipping through that pipe really fast. And so, you know, you can imagine you turn on the water faucet, man, it's going to come out of there quick. So, but what they would do is they'd say, okay, at some point, we'll fire the thruster and stop the water, right? They never flew that. I don't know how they actually get it stabilized now, but I left NASA before I did. Okay, yeah, you have a question?
I was wondering, that's some, like that, the helicopters?
Yeah, the helicopters do the same thing. Okay, you got the body of the helicopter, now you got one blade that's it. Okay, so the one blade is turning this way. Well, you have a torque between you and the blade. Right, because you got drag, you got lift, all that kind of thing. So what you're doing is you're twisting it this way. Well, it's gonna twist you back the other way. So you'll spin fast. Right, so why do they have that tail rotor? Yeah, so what it does is it creates a sideways thrust, so when they're spinning the big propeller this way, they get a thrust this way, and holds your body still while you're turning the propeller. Exactly the same thing. Three-dimensional rotation is complicated, okay, so I'm not really covering it in this class, but I'm sure you've seen, you'll take a bicycle tire and you spin it, you can hold it on the edge of your finger and it'll recess around. It's the same thing. Angular impulse equals change in angular momentum. But in 3D, you get some wild, crazy things happening. Okay? Not in this class, but that weird. So a helicopter is 3D. You got some weird stuff going on in the helicopter. Okay. Any other questions? One of the things that they'll use this for is they have what they call reaction wheels. So you fly a spacecraft, and let's say you wanted to point something at somebody. You want to shoot them or whatever, right? Or, okay, you want to point your satellite, but you want to do it quick, right? They'll use what they call a reaction wheel. So what they'll do is they'll have a spacecraft, instead of firing the thrusters, they have a spacecraft and they have a big wheel with mass. And what they do is if they want it to turn this way, they'll spin the wheel the other direction and they'll go like this. And then when they stop the wheel, the body stops as well. So when you turn the wheel, you turn, you stop the wheel, then it stops. Right? Just imagine, I'm a satellite, I got a big wheel. I hold it still. I don't have any angular momentum. If I spin this wheel, right, it's me spinning the wheel, it's gonna react against me. So if I turn one way, it'll turn me the other way. As soon as I stop it, I stop. So if I turn back, and I stop it, it'll stop. I saw some videos of astronauts up in flying in the shuttle. I can't find it, or I brought it in. It was really cool. They're all in a line, right? They're like this. And then they say go, and they all start doing this kind of thing with their bodies, and they go, like a quarter turn, and then they snap down again, and they stop dead nuts, man. I mean, it's cool, right? Because you don't expect that. And then they flip back like this, and boom, and it's really, you're gonna find that video. But that's what happens with the angular momentum. There are applications for using this kind of stuff, okay? Building toys or satellites or whatever. Okay, let's see what else I had. Here we go. Okay, so here's the jumper. When I ask you jumper. All right. Why am I not clicking? Well, doggone. Help! Did you go? Ah, okay. I asked you what would happen if the blue guy was over top of the, and you're right, it just goes straight up. Why? Because there's no moment. Right, there's no moment. The momentum is all right here, right along the center line. See that? So what'll happen is it just jumps up off the ground. Okay, let me ask you this. Suppose you're a bungee jumper. Anybody bungee jumping here? You gonna do it this weekend? Yeah, I'll see you next month. Okay, so you bungee jump. All right, so suppose this is the platform that you're gonna bungee jump off of. And suppose your bungee jump is attached right there. And you jump off. Okay, you're right over here. Eventually, you quit going up and down, right? Eventually, it stops going boom, 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 boom. right? When it stops going up and down, what are you doing? You just hanging out at the bottom? You're just hanging out down here when it stops going up and down? Is that where you are? Or are you doing something? Well, you're upside down. Okay, down there. Why are you swinging back and forth? You've seen it, right? Well, you should know why. I just covered it.
Yeah, because you're up in the center and stuff.
Right. So what's happening is, where's your center? Right here. This is you're doing some moments right here, right? Okay. Do you have momentum? Yeah, you're jumping this way, and your momentum's getting bigger and bigger and bigger and bigger, right? Until the bungee gets a hold of you. But anyway, the bungee. If you sum, you got isn't that an angular momentum? A momentum times a distance. So you have an angular momentum. You will keep that until somebody takes it away from you. Until you have a moment that takes it away from you, you will keep your angular momentum. Okay, so when you get down here and you quit going up and down, you will have your angular momentum. It'll go like this, back and forth like that. So when you jump straight down, you don't have to jump out, just jump straight down, just fall. And if your body is not over this point, or under this point, I guess, if your body's not under that point, you will be collecting angular momentum, and you will keep it. And you will end up at the bottom going like this, back and forth. So if you have a cliff right here, right, and they strap you onto this, don't you dare let them put you, well, they know what they're doing, I'm sure. Right? But you don't want to jump off center, because if you do, you're going to be doing this when you get finished. Okay. You have to. Okay, you seen the ice skaters? When they start doing this, they pull in. Why is it that they go faster? Why? Why? What did Newton say? Angular momentum, right? Okay, so you got ice skates. Do you have any friction under them? Not right. Right, so you're spinning quick. That's why I can't do it. Because I got friction. And it gives me torque. But if you're on ice skates, you don't have much torque down there, right? So you get yourself spinning like this, right? And so you got an angular momentum, right? You got to keep it. When you start pulling the masses in, that's less moment arm, right? Less moment arm. And so if you have less moment arm, but you have to keep your angular momentum, you got to go faster. So that's what happens. Is you pull in, you go faster. How can you use that? The governor, very good. So you want to make sure that you have a constant speed motor. Okay, and you put what they call a fly ball governor. This is old-fashioned stuff, but you spin it like this, and then you have weights. So if the engine begins to go faster, spin faster, what's going to happen is these balls will get thrown up, and then you connect that up to a valve that controls the flow of fuel to the engine. So if it goes up, they choke down the engine, so the engine slows down. So it's fly ball governor. Okay? A flywheel is very similar, but it doesn't try to. What it does is tries to keep the motion going. Flywheel. There's lots of applications for it. Okay, what you need to realize is, and I also talked to you about the weather, didn't I? Right? At the equator, it's hot. The air gets hot, it goes up. It's hot air rise. Right? So it rises. It leaks a vacuum in, so the air on the ground tries to replace it. Okay, in the North Pole, it's cold. South Pole, same thing. North Pole's cold. It cools the air goes down. So it creates a vacuum there. So what happens is the hot air from the tropics tries to head towards the pole. Right? This is the sinks, the air wants to replace it. Okay? So you get that circulation. Right? Well, on the equator, you got this big moment arm, radius of the Earth. So even though the air's not moving much, then as it heads towards the pole, the moment arm gets smaller, smaller, smaller. So the air has to move faster. So what happens is in the northern hemisphere, the natural tendency is to get winds coming from the west. Right? As it heads north, winds push from west to east. Right? And so then you get these. Right? That's why we always get our cold fronts coming in from Santa Cruz. radiation in from the moon. Yeah, which the natural convection is the, from that. Okay. You look like you're bored. Let's do another problem. Okay. Oh, man, I love this one. You gotta watch this one. If I can get it to come up. How am I gonna get that guy up there? I do. Okay. Oh. Yes. All right. Now we're gonna do. You did? All right. Let's see if I can get this sound up. Oh. Oh, have you all seen this guy? No. I mean, he's really neat. Yeah. Oh.
Or will it go higher? Okay, so versus
Okay,
being shot
so
in the
he's got a
middle
block
when
of
you
wood.
shoot on the side is the question, right?
He's
Like,
gonna shoot a
how
bullet
high will it
into
go
the
in
block of
comparison?
wood. It's gonna
It
shoot
depends on
right
if the
into
bullet
the
stays in
center
the
of
block. And I'm assuming it does. It does stay in the block. It
that.
does
That
stay
would
in the block.
be
Either.
same height. Same bullet,
I'm
same gun.
purely
same
basing
everything.
it on just
Offset.
like an instinct that I have.
I feel like I'm being tricked.
I just feel like you're trying to trick us and that it's going to do something that we can't predict.
I thought the obvious answer is not as high, so I'm going to say higher.
I'll say higher, but it's going to like fly in a different direction or something. So you have
And of course, they're telling you all their
angular
answers,
momentum,
right?
L,
But you-
and you have translational momentum, which is P. Yeah.
You want me to start it over?
Block up
Okay.
and also just goes up. All right, here is the setup. I have a rifle mounted vertically, and we're going to shoot a bullet into this block, right into the middle of it. So obviously the block is going to go flying into the air. But we're going to do this again.
Now, this would be
and
cool.
instead of firing the bullet right into
We
the
gotta
middle
get
of
a
the block,
gun.
we're going
We
to
gotta-
shoot it off to one side. And I want you to make a prediction. Will that spinning block, when we hit it to one side, will it go the same height as this first block? Will it go not as high, or will it go higher? Okay, so versus being shot in the middle when you shoot on the side is the question, right?
Okay,
Like,
then they're
how
gonna
high
go
will it go in
up. This is my
comparison?
opinion.
It depends on if the bullet stays in the block.
So while they're
I'm assuming
giving
it
you
does.
their
It does
opinions,
stay in
what
the
do you
block.
think?
It does stay in the block. Same height. I'm purely basing it on just like an instinct that I have.
I feel like I'm being tricked.
I just feel like you're trying to trick us and that it's going to do something that we can't predict.
I thought the obvious answer is not as high, so I'm going to say higher.
I'll say higher, but it's going to like fly in a different
Will it go
direction.
higher?
So you have angular momentum, which is L, and you have translation momentum, which is P. Yeah. When you hit it in the middle of the block doesn't really spin, and also just goes up a certain height. But when you hit it on the side of the block, it's going to be spinning, so it's going to be part of its kinetic energy, so there won't be as much potential energy. And so the total energy of the system basically has to stay constant, and the kinetic plus potential, which would be the height it goes to, will have to be constant. So if it's spinning and has kinetic energy, it can't go as high. That's my prediction. So my prediction is it'll go up, not as high, but it'll spin more if it's hit to the side. Am I wrong? I want you to think, which do you think is the most reasonable, and then click one of the annotations above. All right, are you ready? Make your prediction in 3, 2, 1.
Give me a, I mean, because I like his opinions because he's telling me energy, blah, 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 blah. Tell me about energy, tell me about momentum, tell me about something that Newton said. So that you would say, well, you know, hey, I'm not smarter than you. Newton said so-and-so, that's what it's gonna be. Right?
A lot of
What I'm trying to
innovations
show
are to start with a question, what if? Or what do you think of this idea? What if we did this? It'd be pretty cool if we could do this. And then every now and then, people get serious about it and say, you know, let's go do this. If you just talk about the general influence of the... Alright, let's watch it. Hopefully I'm not horribly wrong.
The point I'm trying to make.
Derek's giggling north and south right now.
Okay, you have made your prediction. Now,
To say, which way should this company go? Should we build front-wheel drive vehicles or rear-wheel drive? Should we do this? Should we go to the moon? Should we do blah, blah, whatever? You gotta make a decision. You do not wanna make your decision on, I feel like blah, blah, blah. I don't care what you feel like, unless you're new. And you may be, right? You may be the next Einstein. If you are, then fine, you can do anything you want, because you're brilliant. But most of us are not. So what I say you do is the same thing I try to do. And that is when somebody asks me something, I say, well, Newton said this, Einstein said that, whatever, and so therefore it must go higher, it must go lower, it must go somewhere. Right? So the fact that you say, well, I just feel like it, well, okay, then give me the principle. He said conservation of energy, he's talking about energy. Why is it gonna go higher? Okay. Okay. They should rotate. But do they go higher? Sure. Angular velocity, okay, larger angular velocity. I won't disagree with that. You do the tuck, right? If you tuck, divers, right? You go off the diving board and they tuck, so they you get 3 flicks in before they untuck and then slow down and go into the water. So yeah, but we're talking about height, not rotation.
Because I think it would probably take a large amount of wood for the boat to move that whole block straight up, then it would spin.
So what do you say, we'll go higher?
Yeah.
Okay, so he's saying that it takes more energy to raise the block up without spinning. Is that right?
Yeah.
Okay, and so, when it spins, it will go actually higher. Well, okay, so basically he's saying it's less energy to move it this way than it is. Why? Why should they do that?
It's gonna be like, if they do the center mass, it's gonna be like the boat's gonna go in farther in, but the other one's gonna move it, it's gonna have less work. So it's gonna have, you're gonna lose that energy, the angular velocity is gonna be so.
So I hear one that says the same, right? One that says, well, he's kind of on the fence now. Maybe it goes higher, but he's got a reason for it, right? That's the point. I'm not trying to embarrass you, right? I'm just saying, you should have a reason for making the statements you do. Because, if you're working in a company and they say, why is it gonna do this? I mean, you got millions of dollars resting, not on this block of wood, who cares, right? But usually when you're trying to make a decision, you got millions of dollars resting on it. You better be making the right decision. Okay? And I can give you lots of examples where I've seen people make the wrong decision and then they spend a lot of money chasing this rainbow. The unicorn or whatever it is. Okay, so base it on something. So it's not so much whether you're right or you're wrong, but you better be basing your decisions on something. And then when you get into discussions and when somebody argues, well, my gut tells me, well, I don't care about your gut, man. I want to, tell me something else. Okay. So anyway, he has the solution. I'm not sure if this is it or not.
now it's time to find out which block went higher, the one that's shot off-center or the one that's shot right into the center of mass.
So,
Okay, we're just getting set for shooting straight into the block. How you feeling about this one, Dave?
I think this is the one. I really do.
Okay, range is going hot. In 3, 2, 1.
We've moved this block so now the gun is actually firing into the right side of the block. So presumably one imagines that the block will spin anti-clockwise.
3, 2, 1.
So it spins like you
Now
expected.
check out the high-speed footage. You can clearly see that both blocks go to the exact same height, even though one is
How
rotating.
about that?
And that's a bit strange because they were both
Where
hit
did
by
the
the
extra
same
energy
type
come
of
from,
bullet
right?
from the
I
same
mean, that
rifle,
was
so
the biggest
presumably it had the same
argument. Why is he
kinetic
wrong?
energy. And they both
I mean,
go
that
the
was a good
same height,
argument.
so they both have
It's
the
got
same
the
gravitational
kinetic energy
potential energy,
this
but
way,
one
it's also got
is
rotational
rotating.
energy.
And so it has that additional rotational
The guy
energy.
that's spinning has
So one
more
block
energy than
has
this
more
guy.
energy than the other block.
I don't know if I buy that, Dr. Muller.
talk to me.
Yeah, I mean, So you're telling me you just created energy?
Not necessarily created it.
Okay.
So what are you thinking there?
I am potentially surprised.
They're the same height.
Obviously I'm wrong.
They weren't the same height, which is incredibly confusing to me.
Why is that confusing?
Where's that extra energy coming from?
But the fact is that one block clearly does have more energy. You think about them both at the top. One's spinning, one's not. They basically have identical gravitational energy, but one does have additional rotational energy.
How is that possible and why is it happening?
No, explain it to me.
I don't want to give you the answer right away.
I love it when you say that. I don't want to give you the answer. That means you don't know.
So if you can make me a video response, I would love that. Or if you just want to post your idea in the comments below, that'd be great. And I will reveal the correct answer next week. So subscribe to the channel if you haven't already, and you'll find out in a week's time.
After I have time to pour over the footage and consult a very smart man in the subject. That's what you have to say.
That's what impulse tells you, right? Well, it's got the same momentum, right? It's got the mass times speed. Once it embeds in there, it's going to have the same mass times speed, has to. So the mass and speed of this block has got to be the same as they head up. They also have an angular, so they will also have the same angular. That's why it turns. Okay? So from momentum, it will tell you they have to go the same. That's what momentum tells you. Why is the energy wrong? You had your hand up over here. You have a question or an answer? Okay.
So when it shoots the angular one, it starts spinning instead of so like it doesn't get to absorb as much energy, or it doesn't transfer as much energy.
Now you're on the.
Now you get it. Going straight on, it absorbs more of the energy.
Now you're getting it. When it hits straight on, that's exactly right. What happens when you hit straight on, it loses more energy when the bullet goes in. It loses more energy, and that's where the energy came from. It's not like it suddenly appeared. It was always there. It was in the bullet, right? And then the bullet says, "Hey, come with me, and we'll have some energy together." But because of the collision between the two, you transfer the energy to some other form. It goes into bending the wood, breaking the wood, warmth, thermal, it goes somewhere, right? Into the sound, whatever. It goes somewhere, but it doesn't go into kinetic. And so you don't have as much when you hit it dead on as on the side. So why do you lose more energy when you hit it dead on? Well, what's happening is when you hit it over here, this guy's moving back as the bullet goes up, right? So what will happen is the bullet doesn't get embedded as far when you push it over on the side. When you shoot it on the side, the bullet goes in some distance, but not as far as when you hit it dead on. That's right, and the wood is backing up, getting out of the way, and so the bullet doesn't travel as far into the wood. So it doesn't do as much work to convert it over to something else. And so you conserve, you save more. You don't lose as much. Okay? And that's why the energy argument didn't fly. Now, what was wrong with him using energy? What should you have noticed and said, well, I'm not going to use the energy argument? What have I told you about energy? Energy is lost during what? Collisions. Don't you have a collision going on? And didn't I tell you that it's really complicated to figure out how much energy is lost during that collision? But yet you try to use it. But, you know, no harm, right? But you see, that's the problem. He said, okay, energy. Energy looks like an easy principle. Yeah, but you got a collision. You can't really argue energy when you have a collision. Right? What you could do is you could say, at most, it could go this high. But I know it won't go that high. Why? Because I'm going to lose some. I'm going to turn it into a heat or something. Right? Theoretically, it will go this high. if I don't lose any. But I'm gonna lose some, so it's gonna go somewhere down here. So you would use the energy to say, well, what's the best you could do? Well, the best I could get it up, you know, right? So if you're trying to run a contest or something, you say, okay, you gotta shoot the block of wood 10 feet high. You can say, well, maximum theoretical is gonna be 9, so I better get a bigger bullet. Get the idea? Okay, but that was the problem. You know, you started with a valid argument. It's a good argument, right? But you fail to realize, oh, wait a minute, I don't really know what the energy loss is, because there's a collision, and Everett's told me that, man, that's hard. Yeah, it is, man. It's complicated. Get the idea? Okay. You want to do another problem now? Because I think I'm out of video. Okay.
So then regardless of what happens in the process, the optimist and the pessimist is thinking.
Right, because you can't argue it with energy, because you've lost energy. And you know, when you hit it dead on, you lose more than when you hit it on the side. Right? And how would you know that? Well, what you should know is it's a bad argument when you have collisions. Energy is a bad argument during collisions. Okay? So don't try it. So the momentum is the correct one, and there's a guy who comes on and he does all the theory and blah, blah, blah. Okay. So basically what it is if you look at momentum, there's none of this business of, well, yeah, but you lose some. No, you don't. You never lose the momentum. Okay? And so if you give a momentum argument, whatever momentum you have in the bullet going straight up, you're going to have that linear momentum in the combination. So the combination has to go the same no matter where you hit it. Angular, you have some angular because it starts off center. So here's the center of mass of the block. You're over here, you got some angular momentum. You're going to keep it. And that's why it turns when it's linear. Because you got to have the same angular momentum you had in the bullet. Okay? After the collision. Here, same linear. Right? So it's going to go the same distance up. But in one case it will be turning because it has that same bullet angular momentum. Okay? So that's the proper argument to tell that it's going to go the same height. This guy's got all kinds of really cool stuff. I mean, now that I found him, I'm going to use him more. Okay, let's do some problems. Unless you have questions. All right. Okay, how about this one? $200-gram projectile is fired with a velocity of 900 towards the center of the 15-kilogram wooden block, blah, blah, blah. If the projectile penetrates and emerges from the block with a velocity of determine the velocity of the block, Okay. Now, you say this is on the final exam. What are you going to do? Freak out. Okay, no. Is it energy? For the final exams, you're going to say, maybe this is an energy problem. Because if it is, it's a good one. Because the energies are usually short. Quick and easy. Okay? So is it an energy problem? Go through the 3 steps. Number 1, can you find the energy, the work? Can you find the work, the losses? No, why not? There's a collision. And you've seen from the video, man, when you have a collision, you have no idea what's going on. Okay. Energy's out. Boom. Maybe it's an impulse and momentum. What do you need in order to have a good impulse and momentum? You need to be able to get the impulse, the force versus time. And I showed you the trick that you use, right? This is an impulsive force, right? The bullet goes through there. It's a huge amount of force. You agree? So we're going to ignore everything while the bullet's going through the block. Okay, is there something you can do so that those impulsive forces are zero when you draw a free-body diagram? What I do with the 2 cars, I took them both together. If you take the bullet and the block together, what are the impulsive forces that must be drawn on a free body? Are there any? Everybody okay with that? Is friction impulsive? It's equal to mu Kn, right? Or mu Sn or something like that. It's mu S times, is N impulsive? No. Is mu S, no, it's not impulsive. Right? So I'm going to ignore the friction. While the bullet's in the block, I'm going to ignore the friction. Gravity, is it impulsive? No. I'm going to ignore the gravity. Okay? Why? Because the impulsive forces occur, that bullet's only in there for a thousandth of a second or something, right? Friction can't possibly be doing that much in a thousandth of a second. You get the idea? Okay. So I'm going to take the bullet and block together, and then the impulse is equal to zero. Okay? So I think this is a good impulse momentum problem. So here's what I'm going to do. I'm going to take the bullet and block together before the collision and after the collision. Okay, so here we go. What is the impulse? Zero. Because I'm taking them together. Impulse, according to Newton, impulse equals the change in momentum. Right? And if this was moment of the impulse, it would be change in moment of momentum. But this is impulse, so this is change in momentum. What's change? Final minus initial. So I want the final momentum. Okay, so the bullet, after it emerges from the block, can I find the momentum of the bullet? Yeah, because I know the mass and I know the speed. So here we go. And he's going to the right. Let's take right positive. Is that okay? Okay, so we'll say this guy here is positive. So he's going to be 200 over 1,000. Why? Make sure everything's in kilograms, newtons, meters. Okay?